So in today's class, we look at this one important question: how to measure the quality of a design. So as part of your project work, you're going to give me a lot of designs for your projects, schemas and their relationships. How to measure the quality of your design? That is the question. Are there any methods to measure the quality of the design? Say if I go and create an employee table, I put some attributes together and then I say that this makes the employee table. But how good is this grouping? You group some attributes together, is that really good enough? That is the question. How will you analyze that? Do you have any formal measures to measure this? So that is the question in today's class. Say you come out with a design like this. Most of the times the design is done because of the designer's I can say intuition or his own perception. So he groups some attributes and puts it together and says it's a table. But is there any way to measure the quality of this design? So we'll be talking about measures of evaluating designs in our third module. And there are two kinds of measures. One is informal measures, another one is formal measures. So when I say informal measures, there are some guidelines given. Informally, you follow these guidelines to have a good design. Formal measures is they have come out with an entire theoretical concept to evaluate the goodness of your design. So first what we look at is, we look at what are the informal measures for evaluating a design. What are the guidelines given to us for evaluating a design? Guideline 1, it's coming under informal measures. Do not combine attributes from multiple entity types and relation types into a single relation. So when you design a relation schema, it should be very easy for you to explain the meaning of that schema. So we'll go and take a look at a poor design. What is this? What is this poor design? Let me give you a sample here. I have mixed attributes from different entity types into one single relation here. So what are the attributes from different entity types? So you see here, employee SSN, employee name, employee salary is from employee entity. So this is one entity, and department number, department name and department location is from another entity. So when you go and create a table by mixing or combining attributes of different entities, it becomes a poor design. So what are the problems we get with poor design? What are the problems? Say if I have data into my tables like this, what are the problems I get? First problem is redundancy. Say for a department, there can be n number of employees working, right? So this department information is going to repeat. So redundant data is one big issue because of poor designs. And what are the issues you may get because of poor designs? So one is redundancy in data. Another issues, they are categorizing that as update anomalies because of poor designs like this. So what are the update anomalies we will be having? It's three categories: insertion anomaly, and then you have deletion anomaly, and then modification anomaly. We'll be looking at what are these anomalies one by one. Insertion anomaly. What is an anomaly? Anomaly is nothing but a glitch or an abnormal situation. It should not be present in our tables. So we will look at what is this insertion anomaly. Say if I design a schema like this by mixing up attributes from different entities, what I will get? Say if I want to insert the employee who is not part of any department, and an employee has just joined, he is not mapped to any department, then what will be the result here? So you see here I have inserted two employees, but the department, the data is all null because it's missing. We don't have any information for these employees. So we'll have lot of null values populated in your table because of poor design. So what is the problem with null? What is the issue with null? We can have lot of null values like this. Why we should be really worried about this? Wastage of space. We are only focused on conserving space. Say you don't look at 4 records here. Say you have 1 billion records and half of the table is empty. So how much space you are going to waste? So that is one thing, and there are other problems with null. Null gives us so many different interpretations. Null gives us so many different meanings. One thing is, we know the value, but we have not recorded it yet on the database. Say for these employees, we know the values, but we have not recorded it. That can be one interpretation. Another interpretation is, these employees are never mapped to a department, so they don't have department information at all. That is another interpretation. And the third interpretation is, the attribute value is unknown. So when you take a look at the null columns, you get two different interpretations. Whether this row has got anything to do with these attributes that are null. So it really misguides. So null values are not acceptable in your designs. Normally students have this tendency. For instance, if I ask them to do a course registration software, they will do a student ID and then they will do course 1, course 2, they will put all the 100 courses in a line in a column. Say a student 1 can register only in say 3 courses, the other courses will be null. That is one kind of poor design, because you are enforcing lot of null values in your tables. And another thing, if I want to insert a department which is not having any employees, just the department information, then what will happen? Can I really insert this record? Say for this table, if employee SSN is the primary key, can I even insert this record having SSN to be null here? No, it will not even allow you. Then how to maintain the department information? That becomes a problem. So these are called insertion anomalies or glitches when you put attributes of different entities mixed up as a table. Deletion anomaly. What is a deletion anomaly? Say I have again the same table. I have only one employee working for this department scope. There's only one employee. And suppose this employee resigns. I want to delete his data, or I want to remove this employee. So if I go and delete this record, what will happen is, I will lose all the information about department. So this is the only department with one employee. So if I delete that employee, the department information is also lost. Later on, I want to add employees to my department. So this becomes a deletion anomaly or a glitch. So if you are going to have records like this, you will also lose information that you want to keep. Modification anomalies. What are modification anomalies that arise because of this poor design? One thing is, say how many times I have to insert this department information? 1, 2, 3, 4. Again and again I am repeatedly inserting the same data. I should be very cautious that first time if I insert it as scope, next time I should not insert it as SCP. So every time you insert, you should be cautious that whatever that is there should be repeated. That is one problem, modification anomaly. Another problem is, if I want to change the data of scope to SCSC, because of this kind of redundancy, I have to go and modify it in every place. Say if I have 1 million records, you run an update on 1 million records, you'll be waiting there. It's not going to get any immediate output to you. So these are some of the modification anomalies you get because of the poor design. So now we'll go to guideline 2. Since we have understood all the anomalies, guideline 2 in Informal Measures says, design relation schemas or tables such that relations don't have any insertion, deletion and modification anomalies. That is guideline 2. In your relation schema, you should see to that you don't have any such issues. Guideline 3, strictly design a schema that avoids null values as much as possible. Null should not apply to a majority of rows. Tuples in the sense rows. So this is guideline 3 for your evaluation. Now we come to guideline 4. Spurious tuples should not be generated on joining tables. Say if I have two tables, if I join them, I should not get any erroneous records or rows generated because of that. So I will take an example here. Say I have designed two tables like this. One is the employee table having employee ID, name and salary. Another one is the employee phone number table. So for employee name, we'll have phone numbers. So I designed a schema like this. If I go and join this, I should not get any unwanted information generated. A natural join. You know what a natural join is? It joins using the identical column names. So you see here there is an employee name and you consider this to be only employee name. So we'll join it using this. Let me go to SQL Plus. Let's take a demonstration of this. I've already created these tables. Let me go and show you. Select star from M. I think that's the table. So it has got some employee ID names. See here we have employee ID 1 Sam who is getting 20,000 rupees salary. Employee ID 2 is Ram, 30,000 rupees salary. There is another employee Sam with employee ID 3 with 40,000 rupees salary. Now, who are the employees having phone numbers? So let's go and take a look at this. Select star from M_phone. So only Sam and Ram, the first two employees, are having phone numbers here. Employee ID 1 and 2, Sam and Ram are having phone numbers. If I go and do a natural join of this, what will be the query here? Select star from employee, natural join. It's not employee, it's M, natural join, M_phone. So according to my data, employee 1 and 2, Sam and Ram have phone numbers. But when I go and perform a natural join, it says employee ID 3 is also having a phone number. So when you join these two tables, you are getting some erroneous information, which is wrong, right? Employee ID 3 is not having a phone number. That is because the way we have split the, we have decomposed the tables. So such kind of decomposition is not allowed. Now let us look at very important thing, formal measures. A formal measure is nothing but they have generated a theory to evaluate goodness of your designs. So for that we have to understand what is this term functional dependency. Functional dependency is a tool for evaluating your designs in a formal way. That's what they mean. And we have to understand what this functional dependency is. It is nothing but a constraint between attributes in your table. So we'll go and take a look at the actual definition of functional dependency in your books. A functional dependency denoted by X determines Y between two sets of attributes X and Y that are subsets of the relation R specify a constraint. The constraint is that for any two rows T1 and T2 in any relation instance R of R, if T1 of X is equal to T2 of X, then T1 of Y is equal to T2 of Y. So let me go and show you an example, then you will understand. Let's take a very simple table having employee ID and name. And if I am just going to have 112 again here, what will be the name here? Satish CJ, right? So it's very simple. Say if I am again going to have 112 in my table, what will be the value in the right hand side? It will be Satish CJ. No matter how many times I am going to have 1 and 2 on the left hand side, right hand side should be Satish CJ. So then in that case we can say employee ID determines name. Very simple. So let us go and understand that definition. Say I will call this to be T1, row T1. I will call this to be row T2. What they say is when T1 of employee ID, this is T1 of employee ID, is equal to T2 of employee ID, what should hold? T1 of name should be equal to T2 of name. Then we can say employee ID determines name. Very simple. So if you, instead of employee ID, if I call this column X, if I call this column Y, now you will understand that. When T1 of X, when you have a condition like when T1 of X is equal to T2 of X, and on the right hand side, the attribute, you have this rule, T1 of Y is equal to T2 of Y, then we can say X determines Y. Employee ID functionally determines name. When T1 of employee ID is equal to T2 of employee ID and T1 of name is equal to T2 of name, what we can finally conclude? Employee ID functionally determines name. That is the notation for functional dependency. If you go with X and Y, we can very well understand the definition as such. Is this clear? Please understand this. I am not going to explain functional dependency year afterwards. I just say X determines Y determines Z, like that. So it's very simple. When you say X determines Y, when the value of X repeats, the value of Y should also be the same. So here you see this employee ID determines name is true, right? This is true. Whereas, can we say name determines employee ID? Can I say this? Is name functionally determining employee ID? Whenever I give Satish CJ, should the employee ID always be 112? See, there can always be 2 or 3 students with the same name or 2 or 3 employees with the same name in the university. So if there is another Satish CJ, his employee ID will be something else. So when T1 of X is equal to T2 of X, there is no rule that T1 of Y should be equal to T2 of Y. So you can say that this doesn't hold. Name will not functionally determine employee ID. So when I say employee ID determines name, the reverse is not true. Very simple definitions. So that's what they are trying to say. A functional dependency is a constraint between 2 attributes, and that constraint is when T1 of X is equal to T2 of X, T1 of Y should be equal to T2 of Y. Then we say X determines Y. Okay. So we'll take some more examples. SSN determines name. We accept that. SSN is a unique identifier, so when it repeats, name should also be the same. Project number determines project name and project location. Whenever the project number is again a unique identifier, right? When it repeats, the project name and project location will also be the same. So why we have this example here is, it's not just determining one column, it can also determine multiple columns. So you can either put P number determines P name, P location, or you can have a shorter form for this. P determines, say if I call this N, if I call this L, P determines NL. Just to be short with our notations. P is project number, N is project name, location. So instead of putting it like this, I can say just P determines NL. This is also true. You take a look at the works on table in the schemas that we have looked at. SSN plus project number will determine hours in the works on table. Do you all agree? An employee can work in many projects. A project can have many employees. So what is the key on the works on table? It's a combination of SSN plus project number. So together that will determine the hours. Okay. So let us take another example. Consider this schema here. It is having department number, manager for that department is SSN, and then manager's phone number. So we will take 2 assumptions here. Every department has only one dean or manager. There is only one manager for a department. Another assumption is every manager has only one phone. Let's take that assumption. He is not having another phone. So here, in this schema, you have one department having one manager. One manager, because he is so poor, he has only one phone. What are the functional dependencies in this table? What are the functional dependencies in this table? Every department has only one manager. So whenever I give department number 123, what is the manager ID? 111. So department number functionally determines manager SSN. You agree? And what about other dependencies here? Whenever I give the manager phone number, manager SSN, what will be his phone number? The same phone number, right? So here you have 2 functional dependencies in this schema. Whenever you give the department number, you are always going to get the same manager SSN. Whenever you give the manager SSN, you will get the same phone number. So we have 2 functional dependencies. I have given that in 2 different colors here. From this, can we infer more dependencies? From this, can we infer more dependencies? So whenever I say this is the department number, will the phone number also be the same? Because that manager has only one phone. So when the department number 123 repeats, the phone number also will be the same. So there is one more additional dependency that is hiding inside this set. So you call that, you can infer that. What is that inference? When I give the department number, the phone number also will be the same on the right hand side, no matter how many times I repeat the department number. Then in that case we can say department number determines manager phone number. How did you get this dependency? You have inferred that from this set. So F is a set of all functional dependencies on a relation. F is equal to, I give a set of all functional dependencies, and what is this additional dependency? I have inferred that from the set of FDs I have here. So what other FDs are hiding inside this set is the question. How to derive all the FDs or infer all the FDs from an existing set of FDs? Is there any approach to that? Say this is a very small table, so you have only 2 FDs. If I have some 10 columns in the table, which one is determining which and what are the other FDs you can infer? So there is one thing that we have to understand. New dependencies can be inferred from a set of given dependencies. We all agree upon that, right? A set of inference rules will help us infer dependencies in a formal way. So instead of just analyzing and inferring, what we are going to do is we are going to understand a set of inference rules. Using those inference rules, we will be able to derive all the functional dependencies from a given set. So we will go and see a set of inference rules. So we are going to look at a set of inference rules. What is the use of these inference rules? When I apply these inference rules on the set of functional dependencies, I will be able to infer more functional dependencies. That is the concept. So let me again repeat, what is the use of inference rules? I have a set of functional dependencies defined for a table. When I use the inference rules on this set, I will be able to infer more rules. So we have to understand all these inference rules. Very simple rules. Rule number 1 says, if attribute y is a subset of attribute x, then x determines y. What are x and y? You can think of them to be columns in a table. When y is a subset of x, then x determines y. You call that reflexivity or reflexive rule. Rule number 2 says augmentation. If attribute x determines y, so xz will determine yz. These are some rules. So what augmentation says, if x determines y, then xz will also determine yz. Rule number 3, if x determines y and y determines z, then what we can infer is x will determine z. That is called transitive dependency or rule of transitivity. Rule number 4 is decomposition. So if x determines attributes yz, then we can say x determines y and x determines z. Simple decomposition. Third one is union. What is this union? If x determines y and x determines z, then we can say x determines yz. Final rule is pseudo-transitivity. If x determines y and wy determines z, then wx determines z. So these are some of the rules we will be using for formally evaluating tables. We will also be using that in normalization. So we will just go and look at the proof for all these rules. Everything should be proved. We should have proof for all these rules. Are they correct? So the first 3 rules are called Armstrong's axioms. They have another name for this, Armstrong's axioms. First 3 rules. IR1, IR2, IR3. So proof for IR1. If y is a subset of x, then x determines y. How to prove this? So let us go and take a look at an example here. We have a simple table here. I will call x to be both employee ID and name. What is x? Employee ID and name. So you can even write it. What is x? X is employee ID and name. I call that x. Y is a subset of x. So I can say name to be y. You agree? So y is a subset of x. So y can be just name. Now name is a subset of x, right? Now when you have something like this, you say x determines y. You agree that? So what we'll do is, this is x. We'll call this, when t1 of x is equal to t2 of x, then it means the entire thing repeats, right? This is t1 of x is equal to t2 of x. What it actually means is, t1 of y should be equal to t2 of y. So by this, what we can infer? X determines y. So what is x here? This entire thing. When you repeat x, the subset will also repeat. So you can very well conclude x will determine y. Is this proof clear? So you call this t1, you call this t2. What is x? This entire thing is x. When I say t1 of x is equal to t2 of x, obviously the subset will also be the same. So we can say t1 of y is equal to t2 of y. When that condition holds, what you can very well conclude is x determines y or employee ID determines name. That is the proof for IR1. Proof for IR2. What is IR2? Augmentation. If x determines y, we are just augmenting z on both sides of the attribute. So xz should also determine yz. So we will prove this with a contradiction. Let's say we have x determines y and we'll take xz is not determining yz. We'll prove that with contradiction here. So we have to prove this. We'll assume this. Okay, we'll take this. What we have here is x determining y and xz is not determining yz. When you say xz will not determine yz, only when this rule holds. That is, t1 of xz is equal to t2 of xz and t1 of yz should not be equal to t2 of yz. Only then we'll say xz is not determining yz. Is that clear? When you say this is true, only when this holds. We can take an example here, say x, y, z are columns in a table, and according to this condition, t1 of xz should be equal to t2 of xz. So what is that? This is t1, this is t2, t1 of xz is equal to t2 of xz. So you have populated some dummy data there. Now what should hold? t1 of yz should not be equal to t2 of yz. When that will be true? Only when the values of y are different, right? Only then, say if you have only values like this 3 and 4, only then yz is not equal to this yz. Only when you have this will be true. But there is a contradiction here, right? When you have this will also be false. What do you mean by x determining y? t1 of x is equal to t2 of x, then we mean t1 of y should be equal to t2 of y. So by this, we mean these two things should be equal, because only then our assumption here will be correct. So what we end up finally is, this is not true. When x determines y, xz should determine yz. That is the proof by contradiction. Finally, we look at proof for IR3. X determines y and y determines z, then x determines z. Who can prove this? Can we directly take an example? What we say, x determines y. So what does that mean when x determines y in a table like this? t1 of x is equal to t2 of x, t1 of y should be equal to t2 of y. That is x determining y. We will take the next condition that is given, y determines z. What do you mean by y determining z? Whenever t1 of y is equal to t2 of y, what should be the condition? t1 of z should be equal to t2 of z. So when you take a look at this relation, finally what we have understood, x determines z, because when t1 of x is equal to t2 of x, t1 of z is equal to t2 of z. So this we have proved. Very simple. When you say x determines y, this should hold. When you say y determines z, because you are taking this to prove this. When you say y determines z, obviously when this is equal, this should be equal. So from this, what we get is when t1 of x is equal to t2 of x, t1 of z is equal to t2 of z. So we can always say when x determines y and y determines z, we can very well boldly say x will determine z. That is the rule of transitivity. Proof for IR4. Can you go and prove this at least? Decomposition. If x determines yz, then x determines y and x determines z. So what you have to do is you have to take this x determines yz and you have to prove this. Take the ones on the left hand side and prove that. How will you prove that? So let me go ahead with this. Let me take x determines yz. That is given. So from this I can infer this. Yz determines y using IR1 reflexivity rule. So what is y? Y is a subset of yz. Do you agree? Y is a subset of yz. So what you conclude by IR1? Yz determines y. So you take this yz and you come out with this rule using IR1. We have already learned that. So now you have x determining yz and yz determining y. Using transitivity, IR3, what you can say, x determines y. So using this, we have proved x determines y. Can you prove x determines z? Very simple. You again take this. Z is a subset of yz. So you can always say yz determines z using IR1. So x determines yz and yz determines z. So using IR3, what we can say is x determines z. So we have proved x determines y and x determines z using x determines yz and our IR1 and IR3 rules. So you can think about proving the other two things, IR5 and IR6. We'll continue this in our next class on maybe next Thursday.